Now we're gonna sort of switch gears into kinetic molecular theory and changes of state. So kinetic molecular theory consists of 5 parts. It is a model that explains the physical properties of matter, so solid, liquid, and gas, and its changes of state. So the first rule, all matter that is made up of particles is constantly moving. 2, the energy of the particles depends on the absolute temperature. 3, changes in state may occur when the energy of the particle is changed. Oops, typo. The average amount of space between particles increases as the matter moves from solid to liquid and to gas. There are forces of attraction between the particles which become stronger as the particles move closer together. So these are the 5 components of the kinetic molecular theory. And here we have a nice little diagram that explains the changes of state and what they are all called. So when you have a solid that turns into a liquid, it's called freezing. And when you have a liquid that turns into a gas, it's condensing. When you have a gas that turns into a solid, it's called deposition. When you have a solid that turns into a gas, it is sublimation. When you have a gas that turns into a liquid, it is boiling and evaporating. When you have a liquid that turns into a solid, it is melting. One important thing to note about evaporating is that when it is in liquid state, evaporation can happen at any temperature given the same pressure of the atmosphere. So when you have a solid, back to my beautiful drawings again. When you have a solid, it's in a fixed shape, it's a fixed volume. You have strong intermolecular forces. So what do we mean by intermolecular forces? It means the forces between the molecules and not within the molecules. So intermolecular would be here. And intramolecular would be, the stuff that's going on inside. Particles vibrate in position, and there's little distance between the particles. So that's solid. When you have a liquid, there's no fixed shape, but there is fixed volume. And the interparticular forces are relatively weak. There is more distance between the particles, and they can rotate, slide, spin, do a twirl, They can do whatever they want over sort of each other a little bit, and they vibrate. Then you have gas. For gas, you don't have a fixed shape or volume, so they're just sort of all over the place. Interparticular forces are negligible considering because their movement is very free, and it has the greatest distance between particles in all of these 3 states. The particles can rotate, vibrate, and move around. So here we have a graph of temperature against the energy added. So here's an interesting thing to note. Why is it so that the temperature is the same here and here? That is because, when a solid is being, when heat is added, over here, so let's start, when a heat is added to a solid, it's melting. However, when it reaches its melting point at this temperature, when it reaches here, all of the heat that's added, which is basically energy, is used to overcome the interparticular forces of the molecules. So remember my beautiful diagram here about this being a solid and this is a liquid? The heat added is used to overcome the forces here, so that they're broken up to have more space. And that is why the temperature does not change when a solid reaches its melting point. And then you'll progress to a liquid. And also, I forgot. When it's at its melting point, both solids and liquids exist. So you have 2 phases together at this point. Then you'll have a full liquid. Then temperature is increasing again. Then at this point, you have your boiling point. So like the melting point, it plateaus because the energy is again being used to sort of go over the interparticulate forces of the molecules. So here they're being overcome for there to be more space to move around when it's in its gaseous state. And also here you have both liquids and gas. So the forces of attraction are overcome when changing from solid to liquid to gas. Energy is required and used, and this is an endothermic process. So an endothermic process is when energy is being used internally. And for an exothermic process, it's when energy is being released. So this is endothermic. This graph that we have here is endothermic, and exothermic will sort of be the opposite process. So this is sort of the summary of what I just said. You can read over it, pause if you'd like to. Next, we can talk about the Maxwell-Boltzmann distribution. The moving particles in a gas or liquid do not travel at the same velocity. So we have particles here. Not all of them are going to move at the same rate or at the same direction. Oh, let's just say this is a liquid. Kind of looks like a solid, but it's a liquid. Some travel faster and some travel slower. And the faster a particle moves, the more kinetic energy it possesses. So the distribution of kinetic energy within a substance is shown by a Maxwell-Boltzmann distribution. So it's this thing over here. When a liquid evaporates, the faster moving particles are the ones that escape. So let's say this is a liquid. You have some particles that move faster. Let's say this one moves faster. So of course, it escapes its intermolecular forces first, and it evaporates into gaseous state. So because this one escaped, the average kinetic energy of the remaining particles will be lower. And at high temperatures, the total number of particles remains constant at the area under the curve. And the more particles that have higher velocity, you will have an increased average kinetic energy. And one important thing to note is that average kinetic energy is temperature. So here we can look at this graph. Kinetic energy, so here would be the average kinetic energy of this substance, and here would be the average kinetic energy of this second substance. And we can equate these 2 points to its temperature. And as you can tell from this graph, because in later IB exams you will be asked to derive information from graphs, we can say that the temperature of the first molecule is less than that of the second molecule. Now we'll look at a question regarding boiling point. The boiling point of ethanol, C2H5OH, is 78.4. Boiling point of uranium hexafluoride, UF6, is 56.5 Celsius, which is a correct statement at 50 degrees Celsius. So how I like to approach these questions is that I like to sort of draw like a timeline. And we'll put the 50 degrees Celsius marker here. So the boiling point of ethanol, I'm going to write ethanol in blue, is 78.4 degrees Celsius. So what this means, okay, so this is ethanol. It is at 78.4. So what this means is that prior to this, ethanol would be a liquid. And after this, ethanol would be a gas. Then we can look at hexafluoride. I'm going to do it in yellow. The boiling point of uranium hexafluoride is at 56.5 UF6. And prior to this, UF6 would be a liquid, and then after it will be a gas. Let us see which is a correct statement at 50 degrees Celsius. So let's unpack what all of these multiple what each of these selections mean. The forces of attraction between UF6 molecules are stronger than the forces of attraction between the C2H5OH molecules. So what this means is, let's visualize it. For UF6, it would be stronger, like this. And for C2H5OH, it would be like that. Something like that. And so this would be incorrect. So this actually doesn't make sense, because for UF6 we see that it has a lower boiling point than ethanol. And as we've stated before, the lower the attractive forces, the lower boiling point it'll have, because it means that it's going to be able to break through its interparticular forces more easily. If option A were true, technically ethanol should have a lower boiling point, because it has smaller and weaker interparticular forces, so it should be able to break through more easily, but that's not the case. So we can get rid of option A. Option B. The average kinetic energy of UF6 molecules are greater than the average kinetic energy of C2H5OH. So this also is not correct. For this option, we don't even really need to look at their boiling points anymore, because remember, average kinetic energy is temperature. And the question asked us, what is the correct statement at 50 degrees Celsius? So the average kinetic energy of UF6 is equal to ethanol. So again, option B is incorrect. And C, the vapor density of the gas above the liquid is lower for UF6 than it is for C2H5OH. So what does it mean by vapor density? So here, let's say this is UF6. And this is ethanol. Both are being boiled, and UF6 has a lower boiling point than ethanol. And so therefore, at 50 degrees, UF6 should be closer to boiling than is ethanol. And remember, evaporation can happen at any point, and heat is being added because we're talking about boiling point. So for UF6, the vapor density, say it's rising already. Because it has a lower boiling point, it should have actually a higher vapor density than ethanol. Due to its weak molecular forces, because of its lower boiling point, more vapor should actually be above UF6 than ethanol. So again, C is incorrect. And at this point, you should probably just choose D. But we can explain it once more. D, the average velocity of ethanol molecules are greater than the average velocity of UF6 molecules. So this option looks kind of tricky, but it also really depends on the molecular mass. So if we go back, on your exam, you'll have a periodic table. If we go back to our periodic table, and we find uranium. Oh, uranium is here. Uranium is one of the heaviest elements in the periodic table. And so we can deduct through the molecular mass, the larger a molecule is, the less it will move, and not the less it will move, it'll move at a much slower velocity. So through that, we can deduct that the average velocity of ethanol molecules are greater than the average velocity of UF6 molecules. Therefore, D is correct. Okay. Then we're going to look at a question that regards separation techniques. In the manufacture of a commercial drink, a batch containing water, sugar, dyes, and flavoring concentrates became contaminated with an unknown solid during the mixing process. State the type of mixture that best describes this batch. So, let us break it down. So we have things containing water, sugar, dyes, flavoring concentrates, and also an unknown solid. So immediately we can see different phases. So this mixture is heterogeneous. Draw a labeled set of apparatus required to isolate the solid particles in the mixture. So, as we can see, there is a solid, and through this we can assume that it is not miscible because it has different phases within. So, when we have a solid within a liquid, within a solution, and it also says to isolate only the solid particles. So, I think we can tell that we can use filtration. So if you really were to draw one, you have a funnel, you have your filter paper, you have a beaker, and you have your liquid coming through. And then the residue would be your unknown solids over here. Okay, now state the method that could be used to isolate the dissolved solids such as dyes and flavorings from the mixture. So here it says that they are all dissolved, so this is a miscible, you have a miscible situation. And what we can do is we can use evaporation. Why? Because it says to separate the mixture from the dissolved solids. So it really doesn't say you have to isolate all of these individual thingies. That's the next question. So we can use evaporation. I don't need to write it here. We can use evaporation because they have different boiling points. And all of the other parts of the mixture can be evaporated and leaving these. 2. State the method that could be used to separate the dyes and flavorings once they have been isolated. So according to the answer key, it really says recrystallization. But I think for the dyes, after recrystallization, you can also use paper chromatography. So for recrystallization, because you're trying to separate a solid from its impurities, so first you can use recrystallization. Then, as we've seen from paper chromatography, your stationary phase will be the mixture, and the dyes will be the mobile phase. So you can separate that onto your chromatography paper. And that's it. Thank you for listening. Thank you to my wonderful partner who's made the slideshow. All credits to the practice questions belong to the owner. Thank you so much, and we'll see you the Wednesday after the next Wednesday.